So here is a question in which we need to implement a simple tree. So basically we need to create a family tree, and it should have it should have persons as objects, and so that's what we need to implement. We need to implement a very simple tree. So first let's just look how we are going to implement a tree. So basically we will make so in the tree each person would be considered as an object, and each object would have three attributes. So one is its name, okay, which is most important, the person's name, and then we will assign a node number to each of the person, and then we will also store the parent's node number. So here if we take this person, his name is X, his node is 1, his node number is 1, and his parent's node number is 0. So basically if you take any object, let's say you go for Y, so you know how it is connected to the tree by the parent node. So parent node number. So if you see parent node number is 1, you know it is connected here. And now if you go here, so his name is X, and this node is 1. So now if you check the parent node number of this, it is 0, so it is connected here. So this is how it is. So this is how we are going to connect the trees. So each of the object is going to know its node number and its parent's node number. So anytime you want to traverse through this tree, you can just go from the bottom, and then you will eventually reach the top by tracing back through the parent node number. So this is how this tree is connected. This is a very simple tree. So we are implementing it like this. And now let's see how we are implementing it in the code. So in the code we are creating a class called person, and this is next node. We are setting that to 0. So next node, so what we will do is each time we need to make an object person, we will automatically assign the node number to it. So we need to keep a track of what should be the next node number. So now currently when the program is not started, it will not have any node. Okay, so the first node number will be 0. So head will have node number 0. So we will keep next node as 0. And then we have init function, and in the init function we need to take in name and parent node. So so if you have to create a person, what you should do is you need to give his name and also who is his parent. So you need to give the parent ka node number. So this is how we create a person. So we pass in name and parent ka node number, and self.node we will so now we need to assign a node number to this person. So that we will take from next node. We are tracking this here, and after we assign it, we increment it. So person dot next node plus equal to 1. So we will increment it. So next person will get 1, first person will get 0, then 1, then 2, it goes on. And then we will store his name from what we are taking in, and then also the parent node we will store from what we are taking in. So I guess that is clear. So after creating an object, so this is an object. So now we need to create a family so now these are just the nodes. These are just one circles of it. So now we need to integrate all these circles together. So for that we will create family. In family we will have, this is the most important thing, we will have a list of all the family members. So this list here will contain all the family members object. Okay, it will contain each person. Okay, so it will start with head, the first member will be head, then each of the node, all the node objects. So this list is going to be a list of objects. Okay, and then now we will go for the def init of it. So to create a family, we are keeping it simple. You just need to enter the head's name. So if you are gonna enter the head's name, we will do self.head is equal to person. So we are calling this because head is also a person. So we will call the person class. We'll create an instance of it, and then we will pass in the head's name that we took from here So this will come in from here, and then we will pass -1. So what is the thing is, head is not gonna have any parent. Okay, so we'll take it as a convention that we will go for you can take it, you can keep anything. Okay, but I've just taken -1 for simplicity. So the head is gonna have parent -1, does not exist. Okay, so after that we will go so after creating that person, after creating head, we need to put him inside the family list. So we will do self.fam.append self.head, so he goes into the list. So this has the first family member now. So after doing this, we will go for so now we created a family. If you call family with the head name, you can create an instance of it. Now after creating this, we need to add children. Okay, so now the next function is produce children. And so basically you can, so you first you will have to produce children for head, and then you produce these two children, and then for this person you again need to produce children. So what we will do, we will define a function such that you can produce children for any of the object. Okay, so so any of the person's object you can produce children. So what we will do, define produce children, and for this we will pass in the name. So after you pass in the name, so this name is name of the parent. Okay, so you need to create children, first you need to tell whose children it is. So you create, so you take in the name of the parent and then children names. So in children names you will pass in a list of all the children's name. So I guess that is clear. We'll first take the parent's name, and then we'll take a list of all the children's name. And after that we will just reverse this list. Okay, we will reverse this list for, so that even if you don't reverse the list, it's gonna work. Okay, but if you reverse the lists, the next loop is gonna run for less number of times, because generally you will start adding children to the latest generation. So you will add children to Y, and then first you will add to X, then you will add to Y. So like if you're gonna come from head, it's gonna take more number of iterations. But if you're gonna come from back, it's gonna, like most of the cases, on an average, it's gonna take less number of iterations. So we will just come from the back, but it's not required, like it's not compulsory. You can come from front, it will still work. So now we have taken in the parent's name, but now, but what we need to actually get is, we need to get its node number. Okay, so if you have to create children for X, you need to get X's node number, which will be 1, so that you can create an object Y with while if you have seen, while creating an object of person, you need to pass in the person's name and his parent node number. So so with X, if you take in the node number 1, while creating Y, we can say Y comma 1. So parent node, we will pass in this person's node number. Okay, so basically now we got in its name. From this list we will take the object, we will find the object in this list which has this corresponding name. So for E in the reversed list, we will see if E dot name is equal to name, so this name. So we will check which object has the name that has come in. So after, if we find an object, we will do parent node. We will create a temporary variable parent node, and then we will say that is equal to E dot node. So this object which we found here, uska node we will pass into the parent node variable, and then we will break the for loop. After that, what we will do for E in C name, so there are many children. Okay, so you can see here this list, there are so many children. So for each children in C name, we will create a person. K is equal to person E comma P node. P node we took it from here, parent node. So E will come from the children name list. So we'll create a person for each of the names in the C name list, and then we'll append it to our family list. So now you have created. So now if you call this produce children function for one person. So what we'll do first, we will create for head, we will put the head's name, and then we will say x and y, x and k in the list. So we will create these children, and after that we will give x's name, and then we'll tell children list is containing y and z, and then we'll pass in that, and then we'll create these children. So you can just keep creating childrens like this. So this is how that is done. So so now basically we are pretty much over with the construction of the family. Now the problem statement asks us to provide with some methods. Okay, so now we are gonna do those methods. So from here the methods start. So the first method is head of the family. We need to return the head of the family. So inevitably the first person that is gonna go into the fam list is gonna be the head. So we will just do self.fam 0. Remember that this is an object, so we need to do dot name to get the string. Okay, so we'll get the name string here, it will get printed. Head of family is done. Now let's go for all nodes. So the next function is we need to print all the members of the family. So to print all the members of the family, what we will do, we will iterate through this list for e in self.fam, so this list, and then each of the object we will print the object's name, e.name, we printed it, it's done. The next one is searching for a person, if he is existing in the family or not. So this uses myFam.parent. Okay, so this myFam.parent is here. So we will come back to this function later, after we cover the parent function. So now we'll go to allAncestor function. So allAncestor function, what we need to do in allAncestor is we need to, like if you give y, it should display x and head. If you give x, it should display only head. If you give k, it should display only head. So this is basically a small subset of the parent function. In parent function, if you say y, it should just display x, and then if you just if you put x, it should just display head. So first we will cover the parent function so that we can easily go to allAncestor after that. It's an extension of it. So now parent function, so in the parent function what we will do is we need to take in the name. So we need to take in y. So if we are taking y, then we should return x, correct, right? So first we need to know whose parent we need to find. So for that we will take in the child's name, whose parent we want to find, and after that we will reverse the family list. So fam is equal to reverse.self.fam, it's reversed. After that we will go and we will in this list we will again just find the person, we'll just find the object with this name that we took in. Okay, so whose parent we need to find, that person's object first we need to get it. So we'll go and we'll see if e.name is equal to name. If that is matching, the name is matching, we'll take that object from the reversed family list and store it in a temporary variable. I have just arbitrarily named it no. Okay, so we'll keep that object here, and from that we will take the parent node. So basically what we did is we say the person gives in like the user inputs y. I want to know the parent of y. So first we went in the list and found where is y. So after we got the object y, what we did is we saw what is its parent node. So parent node says 1, and we stored that in a variable. So no.pnode, we took the parent node. So parent node is now 1. Parent node is 1. So now what we do is now we search this tree and see which person's node equals 1. So x person's node is 1. So we will search that. So we search that for e in fam, e.node is equal to parent node, which we took here. So if this person is found with node 1, so parent node here is 1, here also it's 1, here node is 1. So we found this person. After we find this person, what we do is we return the name of the person. So we will do e.name. We return name of this person. After that the next function is allAncestor function. In allAncestor function, the same thing we do. We need to first take the same stuff. We need to take in one object and then find its parent first. Okay, and after that we will find that person's parent. So we'll keep continuing until we reach head. So the first few steps are same. First we reverse the list, and then after that we see for e in fam the same thing. We are just finding which node has this name. So we'll do e.name equal to name, and then we will store that object. When we find the objects, the child's name, we'll store that in a temporary object no, and then we'll break the loop. So now in this we will I've just restarted the recording now. So now for all ancestor function, we get that person ka object. After we take that person ka object, so basically now if we want to find ancestor of y, we will find the object y. After taking the object y, we will store its parent node in current parent node, which will be node.parent node. So we will take this person's parent node, which is 1, and we'll store it in a variable. So now the same stuff we are doing what we did for parent. Now we will go in the list and we'll search we'll search for a node which is having node number as the current parent node. So after we find it, okay, we find this person X. He's having the same he's having the node number as 1, which is what we wanted here. So we find this person, and after finding, we print X, we print his name. So first we print his name, e.name. After that, what we will do is we will not break it. We will change the current parent node. So this person's node, X's current X's parent node is 0. Okay. So now we will tell that current parent node is 0. Okay, so now next time when we go into the loop, this loop, we will search for a node with current parent node as 0. Okay, so we will find this head person who is having the node as 0, which is the current parent node. So the thing is, we will just keep going like this until we reach the last element in the family list. Okay, so by the time you go to head, this will inevitably stop because reverse family list will be over. Okay, so this is the thing we do. We create a variable called current parent node, which will first store this person y's parent node, which will be 1, and then after we find this person, we will print X, and then we will change current parent node to 0. And then now next time when we come, we will find for a person with node 0, and when we find that, we will print it. And when inevitably you call any person's ancestor, head will be ancestor of everybody, and after head the list is done, so it will the function will terminate. Okay, so this is how we do ancestor. We come from back and we keep changing the current parent. Okay, and so the parent is now over. So now there are two functions left. One is the depth function, and then we have searchNode function. So first we'll cover the searchNode function. To search the node, we will pass in the person's name, okay, who we want to search, and basically we need to return if he's there in the family or he's not there in the family. And if he's there in the family, we'll just tell this person is child of the parent name. Okay, so we could have actually written code for this, but we are gonna use a simple logic, and then we are gonna use a shortcut for it. So basically, if we find the person, we will call the parent function, okay, self.parent and name. Okay, so what we will do is this parent function here, if you pass in a name which does not exist in the tree, okay, then this is gonna return an unbound local error. Okay, so what we will do is we'll call this function, and then if this function, when we call this function, this name which we pass in is not going to exist in this will return an unbound local error. What we'll do, we'll handle that error and then print not a member of the family. So we will try this, we'll try to find this person, and then if this function is going to return an error, we'll handle that error until he is not a member of the family. So this search node is as simple as that. After that, we will go for depth. So basically in depth, what we need to do is if they are going to enter y, we're going to say y is in the third generation of the family. If we are going to say x, we'll say x is in the second generation of the family. So that's depth. So to find depth, what we are going to use the same logic, exact same logic as ancestor, because functionally these both are the same thing. You need to go back, and then here there in ancestor you need to print this and then print this. Here we need to count this and count this. So at the first, like, we will starting from here, so we will initialize count to 1. Okay, now if we go back and then we find this, we are not gonna print it. It's the exact same code from here, from fam.reversed. We are taking the same thing from fam.reversed here, except that here we are gonna print e.name. Here we are gonna increase the count. Okay, we'll increase the count. So we'll increase the count, we'll keep increasing it, and then with the time we reach head, the program the iteration should stop automatically, because it's the end of the reversed list. That's why we are reversing list here. So we will do that, and then after we finish through the iterations, we will say the name which we took in, whose generation we are finding, belongs to how much the generation of the family. Okay, we'll print that. It's done. So we have now completed all the methods. Now we need to create user interface, which is kind of very easy to do. So what we'll do is first we will create, so this is the main function. We will do, we'll just say we'll build your family, and after that we will take in the head's name. After taking the head's name, what we'll do is we will create an instance of the family, family class. We'll create an instance of the family class here. So we created an instance class instance called my family, my fam. So we take that family and head name. So with this init function has only head name, so we'll pass in head name and create a family. After creating that, after creating the head, we need to add children now. So what we'll do is we will call a function called produce children, and that is defined here. So what we will do is we will take in this, we will keep taking in parent's name. So first they will enter head. Okay, head will have a name, some name. Okay, they'll enter head's name, and then they will whatever they gave here, head name. So they'll enter head name, and then they will go ahead, and then what we will do, we will create a list to store the children name. So we will go, and then we will enter, they'll enter the children name. After entering one children name, we'll append it to the list, and then we'll ask, press -1 if you wanna stop entering children to this person, or you can create more children to this person by pressing 1. So if you press 1, again we will start this, and we will take in more children name. So we'll keep taking children name. By the time children are over for this person, we'll enter -1 and then exit this loop. After exiting this loop, we'll ask if you wanna enter children to some other person. If you enter 1, you can do that, like it will again ask this, or else you can enter -1 and exit this. So what the thing is, first we'll create for head, and then we'll put in x, and then enter y and z. So we can just keep continue. We can just user can just keep building it. So that's done. So I guess so that's the produce children function. After that, we will create a simple menu driven program. So in this menu driven program, we'll give all the methods that we need. Okay, produce children, know your head, and everything, basically everything that we have done here. We'll just create an interface to use that. So call it appropriately. Some functions could be called without any arguments, and some functions should be called with an argument of name. So take in the name and call it. So this is very simple. And then we'll give an eighth option to break the loop. So we'll just break the loop. So I guess this is done. So this is the program where we have created a very simple tree with and connected it through node numbers, which we only created. Generally while properly doing the data structure of tree, we will use pointers, and then we will use a recursive approach. But here we are going through an iterative approach, and also we are we are itself defining the node by simple integers, so that we are keeping it as simple as possible. So thank you.